it's 1:20. Okay, so we'll get started. Let's see, upcoming events. We just have, we're done with the first exam. So next up is homework number 4, which I mentioned last time I've postponed from this Friday to next Monday. I'll finish talking about optical telescopes, visible light telescopes today, and hopefully, or at least get close to it. I will finish talking about them, but then I'm going to show you and talk about some of UNC's observatories because we have a wide variety of them. Might be a fun topic, and I don't know if I'll get through all that today, but I'll see. Then next time we'll tackle radio telescopes and as much of space telescopes as I can, and whatever I don't get through with space telescopes, I'll put up a video so you can finish that up. That's the plan anyway, so homework 4 on Friday. All right, before we dive into the warm-up question, does anyone have any questions about anything?
Professor, I think a lot of us had questions about, we saw adaptive optics on the WebAssign homework and we weren't sure what that did.
That's today's topic, so yeah, we'll hit that today, almost right away.
Okay. All
right, so let's do the warm-up question. Now, last time we were talking about the advantages of using large telescopes, fell into 2 categories, light gathering power and resolving power. This question's on light gathering power, and tomorrow I'll give you a warm-up question on resolving power. So let's take a look at this one. UNC's 4-meter diameter SOAR telescope, which we'll talk about today. And you can see here, or black and white anyway. I'll put up a color picture in a little bit. It can accomplish the science of a single 0.4 meter diameter prompt telescope, one of these that you're using in the lab. Well, this is our Chile site. It's still closed for COVID, but it will be reopening probably within about a week. But anyway, 4-meter diameter telescope versus a 0.4 meter diameter telescope. The large telescope can accomplish the science of one of the small telescopes in what fraction of the time? That's the question. Okay, I'll give you 15, 20, 30 seconds. Over 100 of you, 112 of you here at the moment. Can we push this up to 50? No, it's bold. We're very far from 50 at the moment. 44. Get engaged, people. Yeah, 50 was too ambitious. I'm going for 45 now. There we go. Okay. So let's take a look at the values. Pretty good. Let's look at the histogram. We'll go logarithmic. So we have some people who answered 100, which is almost right. Some people who answered 100th, which is correct, and they just forgot to flip it over. And then some people answered 10 and some people answered 1/10. Those are the range of answers that I expected. We have some other stuff scattered in here as well, but that's basically it. And someone got cute and entered 100 million. So I'll cut it off at 1,000 there. Okay, so yeah, the one telescope is 10 times bigger than the other, hence that factor of 10, but that's the diameter. So what's the question here? It will accomplish the same science in what fraction of the time? So the science you can accomplish is tied to the collecting area, which is proportional to the diameter squared. Area is proportional to radius squared, so it's proportional to diameter squared. So if it's 10 times the diameter, it's 100 times the collecting area. And so you can accomplish the same science in 1/100th of the time, since you're collecting light 100 times faster. So that explains all of our different answers from 0.1 to 10 to 100 to 100th. But 1/100th is the right answer. And I just explained it in words, but let me put it up here in math, taking a few extra steps. If you're still having problems with the ratio, thinking through things in a ratio sense, the light gathered by SOAR is proportional to the diameter of SOAR squared. That's a large telescope. Light gathered by prompt is proportional to the diameter of prompt squared. So
Can you minimize the window?
Yep, thank you. So the ratio of those two is the diameter of SOAR over the diameter of prompt squared. So 4 divided by 0.4 squared, that's 10 squared, or 100. Yep. And so you can accomplish the same science in 1/100th of the time. All good? Okay.
Can you put that back up for just a moment longer?
Yeah.
So wait, I'm kind of confused why 100 isn't the answer at the end of the day.
You collect 100 times more light in the same time, which means you can accomplish the same science in 1/100th the time. So we talked about two ways large telescopes are used. One is, since you can collect light so much more quickly, you can look deeper, fainter than ever before, pushing the cutting edge. But often they're used in this other mode where we do the same science that we were doing on smaller telescopes, we just do it more quickly because we're collecting the light so much more quickly. So if I ask you how much more light does it collect, the answer is 100. But if I ask you, in what fraction of the time can we accomplish the same science as on the small telescope, it'd be 1/100th.
Okay, that makes sense. Thank you.
Okay, so next time it'll be a resolving power question. Okay, last time we were talking about atmospheric blurring. We had gotten through that, but then we started talking about ways that you can beat atmospheric blurring. The atmosphere typically blurs things out to 1 arcsecond. The light, it's coming through our atmosphere. The atmosphere acts, as we talked about in much greater detail last time, as a bunch of low-powered prisms scattering the light, and prisms, or lenses, prisms, however you want to think of them, prisms, lenses, they scatter blue light more than red light. You see the red light is deflected less, the blue light is deflected more. So as light's coming down through the atmosphere, blue gets scattered all over the place. So one way that you can beat atmospheric blurring, or at least mitigate it, I'm gonna introduce 3 or 4 techniques here. One is just go red, go to longer wavelengths where the atmosphere scatters the light less. If you go all the way to radio, it's outside of the visible band, but that's like beyond red, you have infrared, beyond that, you have microwaves and radio. You go all the way out there, it's like there is no atmosphere. You get the same result as if you were in space. Second option, well, I should say about going red, when we talked about telescopes and resolving power, the longer the wavelength you look at, the telescope blurs it out. So if you want to mitigate atmospheric blurring, you go red. If you want to mitigate telescope blurring, you go blue. So those things work against each other. There's a sweet spot where you're going to have the best you can possibly do with that telescope and with the atmosphere. But that may not be where you have to be to do the science you want to do. The science that you're doing may have to be done at particular wavelengths, and it may not be in that sweet spot. So then the next option is to go up to higher elevation and get above as much of the atmosphere as possible. And I showed you some of the world's largest observatories, not all of them, but just kind of a interesting subset of them. Again, Mauna Kea here at 14,000 feet. And we said you can go even further by going to space, and we talked about the Hubble Space Telescope and how it's not the biggest telescope in the world by far, just a 2.5 meter diameter telescope. But if you get above the atmosphere, you can take advantage of its diffraction limit, which for visible wavelengths is about 0.05 arcseconds, about 20 times better than the 1 arcsecond seen that we normally have from the ground. So not as much light gathering power, but no atmospheric blurring. And I forgot to put this up. This is an example. Maybe I'll make it big now. An example of this, here's a star cluster as viewed from the ground and as viewed from Hubble. So you can see there are hundreds, maybe even thousands of stars there, but from the ground, you don't notice that because a lot of them get blurred together. This is 1 arcsecond blurring, and this is probably 0.05 arcseconds blurring. Okay. Now, of course, when they first put Hubble up, it was worse than the ground. They had miscalculated, misengineered. And you don't remember this, it was before you were born, but you may have heard about it. This was a very expensive mission, and it went up and was a total failure. It was blurry. But Hubble is designed to be serviceable by the space shuttle, which we don't fly anymore, so it can't be serviced anymore, but back then it could be. So they went up and they fixed it. Basically put eyeglasses on it, gave it a lens to correct for the miscalculation they made. Big fiasco, but since then it's turned out to be just one of the great success stories of space-based astronomy.
Professor, you said for atmospheric blurring, use blue light?
No, if for atmospheric blurring, you want to go redwards. The redder you go, the less the atmosphere blurs, but the more your telescope will blur. We talked about the resolving power of the telescope, independent of the atmosphere, just the telescope, since the mirror has edges. You may remember the longer the wavelength you go to, the blurrier it gets due to the telescope. So there's no perfect solution to, the atmosphere is usually the bigger problem. So you normally want to go redward, but if you go too far red, the telescope is going to become a problem. But you can always go up, and then you're just limited by the telescope. Now, so the third technique, it's really two techniques. Active and adaptive optics. We'll spend probably half the class talking about these two things. It's maybe 3A and 3B. Adaptive optics is the really cool stuff. And we know the atmosphere is blurring the light. It's pushing it around and magnifying and demagnifying it on very short time scales, 1/100th of a second-ish. But we can track that. There are devices that we can build, and I'll show you, that we can attach to our telescopes and track how the atmosphere is pushing the light around and then correct for it in real time. If we can track it and send it to really fast computers, we can send commands to little mirrors behind the telescope that undo much of the atmospheric blurring. So we can actually untwinkle the stars using technology, which is pretty cool. And we're not the only ones to do it. The military developed this technology before us. They're looking through the atmosphere too. They're just looking in the other direction. And the spy satellites, you've heard they can read a license plate from space. That's true if they can de-blur the atmosphere. So they developed this technology long before we did, and they didn't share it with us, of course, but we've gotten pretty good at it. They're probably still better, but who knows? But we've gotten pretty good at it. So that's the really cool stuff. Maybe I'll say cool. But as we were developing this, now once we develop this, we can do better than an arcsecond. We can get down to close to, not exactly, but close to the telescope diffraction limit. But we realized that the telescopes that we were building were kind of sloppy. They were built to be good enough to do 1 arcsecond, what the atmosphere would give us, because we never really anticipated developing the technology to do better. Once we developed that technology, we realized we were making some bad engineering choices on some pretty basic things. And that's what active optics is about. It's really just about good design considerations. Compared to adaptive optics, this is the boring stuff. But as is often the case, boring stuff is important. So there are 3 things here, 3 engineering design improvements that we had to make to our telescopes so we could take advantage of adaptive optics. So let's start with those 3 things. So the first is dome airflow design. So when we're talking about the atmosphere, here we have light coming down through the atmosphere, and you can see the light's getting more and more wobbly as it goes through these atmospheric cells. One thing that helps is good airflow. If the atmosphere is moving, there's nice flow of the air, it doesn't break into these pockets, and you have better seeing, less atmospheric blurring. But even on a great night, the light can make it all the way down to your dome, and your dome is trapping air. You know, it's an enclosure, and so in the last few feet, last few meters of the journey of that light, it goes into this enclosed space where the air is trapped, not moving, and it's broken into pockets, and you can have what we call dome seeing. So you have two types of seeing. You have atmospheric seeing, which we can't do anything about except for the adaptive optics. And then you have dome seeing. And that's your fault for building a dome that's trapping the light. So we've gotten around, this is Gemini, which is the American astronomy's biggest telescope at the moment. And there are two of them, one on Mauna Kea in Hawaii and one mountain away from the Prompt telescopes in Chile. And if you look at this dome here, it's very open. So the bottom part, they call it the skirt. So at the beginning of the night, raise the skirt so the air can flow through, and also the slit is very wide. So it folds up and you lose most of your dome, and air can just flow through and eliminate the development of pockets and stagnant air. Many telescopes actually have fans running across their mirrors as well, keeping the air moving in the telescope apparatus, but this helps tremendously. That's one thing you can do. The smaller telescopes, like our Prompt telescopes in Chile, see, I have a little animation of this. I think I put it up before. Let me just grab it again. These use clamshell domes. Here it is. So at the beginning of every night, the dome opens completely, and there is no dome during the night. Now this comes with other challenges, because the wind can push on your telescope. The more you expose your telescope to the air to have good airflow, that air can also push on your telescope, blurring your images. So, you know, there's all sorts of trade-offs always. But this is another option. The big telescopes, they can't make clamshells this big, but the small telescopes, we can just open them up completely and don't have to worry about dome seeing. Okay, that's dome airflow design. Again, fans, even the Prompt telescopes, they come with fans. You can see them mounted here to help move the air in the dome. We can move an entire enclosure's volume of air in about 3 minutes. And the telescopes, they have little fans on the mirrors as well. Okay, number 2 is mirror temperature control. And by this, I'm talking about the primary mirror, the large primary mirror. I meant to say this more for the third one, but they both refer to the primary mirror. Anyway, so you have a large mirror, or any mirror. We don't do this on small telescopes, but on large telescopes we do this. You have a mirror. In fact, the one I put up here, this is the mirror for the SOAR telescope, which was the telescope in our example in the warm-up question. And it's designed to be a perfect parabola, but under real-world conditions, it may not be a uniform temperature. Maybe this region over here gets a little bit hotter than normal. Maybe this region over here gets a little bit cooler than normal. Maybe this over here is hot. And glass or glass composite that this is made of, it will expand and contract with temperature, like almost all materials. So this region here of the glass expands, this contracts, this expands, and we're just talking small amounts, microscopic amounts. You wouldn't notice it with the human eye, but the light that's coming in, visible light, is hundreds of nanometers. And so the surface of that mirror has to be perfectly parabolic to hundreds of nanometers. Actually, you want it to be about 1/10 of the wavelength. So tens of nanometers typically. And if I have a region here, even if just 1/10 of a degree hotter or 1/10 of a degree colder, that will cause distortions in the mirror of that scale, of the scale of the wavelength, and then you won't get good focus. Instead of bouncing and going to where it's supposed to, it'll bounce a little bit off, and you'll be out of focus. So modern telescopes, large telescopes anyway, medium large telescopes, they have heat sinks attached to the back all over the mirror, and allows, if you have a region that's a little bit too warm, it allows that to flow out. A region that's a little bit too cold, it allows energy to flow in. It's attached to something that maintains a uniform temperature, preventing these kinds of temperature distortions to the shape of the mirror. Now, an everyday example of this, I'll put that up, but let me just put what we call this is a heat sink. Something that's attached to that maintains a perfectly uniform temperature is a heat sink. And an everyday example of that is just the road that you're driving on. The ground, so you have highway, you have pavement. Pavement will expand and contract. But the ground acts as a heat sink. It's not perfect. The ground does warm up and cool down, but it does so more slowly than the air. A bridge is not connected to the ground except at the end points, but the rest of the bridge is just touching the air. So a bridge is an example of road that's not attached to a heat sink compared to the ground. And you have these huge temperature swings, and so that causes the road on the bridge, the concrete, to expand and contract a lot more. And have you ever noticed when you go over a bridge, you hear the boom, and then when you leave, boom? There's little gaps, little spacers, you can see it here, that they put in the bridge, knowing that it will expand and contract a lot more than the rest of the road because there's no heat sink since it's not attached to the ground. And so imagine building a bridge in winter and laying this down with no gaps. In summer it expands, and then you get cracks and you have to do all the maintenance and repair work. So they build little spacers there so during summer everything can expand but not crack, and during winter those gaps open up again. Not so much that your tire falls through or anything, but you do hear it as you go over them. Okay.
Also why there are often signs saying beware of ice on bridges, because the temperature can get extremely cold as opposed to just on the ground.
Yeah, we all know this. I grew up in Pennsylvania, so we all know this up in the north. But when I moved down here, you're not as sophisticated winter weather drivers as we are up north, because you don't get the opportunity that much. And it's usually pickup trucks, because it's just the weight distribution of them. A pickup truck with nothing in the back, the bridge will freeze first, and then they'll slide all over the place and cause accidents. You gotta be careful. Okay, and then number 3 is mirror shape control. So that's mirror temperature control. 3 is mirror shape control. And this one, I meant to write it here. This one I'm talking about the primary, and I have to point that out because when I talk about adaptive optics, we'll talk about little mirrors that change their shape, undistorting the atmospheric distortions. This is different. Here I'm talking about the primary mirror, and what's going on is gravity. These things are designed to be perfectly parabolic as they were manufactured in the up position. You know, they're laying flat, looking up, perfectly parabolic. But if you take that and then tilt it on its side, gravity pulls on it differently. Again, you only have to room the parabolic shape to tens or hundreds of nanometers, and it doesn't focus well anymore. So what do you do? Because once you tip this giant piece of glass up, yeah, it's going to bend at that level, if not more. So what they do is they make the mirrors really thin. Again, here's the SOAR mirror, and you can't really see it here, but it's 4 meters across, but only 4 inches thin. We made this, we hired a company to make this in Connecticut, and then we're very nervous because you have to transport it all the way down to Chile. And that's pretty thin. 4 inches sounds like a lot, but it's pretty thin compared to a 4 meter extent. But you get it up the mountain and it was fine. And we make them thin because we put them on a bed of pistons, actuators. Under SOAR, we have 128 of these. And it takes a year. You can't use a telescope for the first year because you have to calibrate these pistons. When it's looking up, the pistons have to all be in a particular position to get that perfect parabola. And you test it, by looking at stars and saying it's blurry, and you try different things until it's crisp. and then you move the telescope into some other position, and it's blurry again, and you figure out new ways to adjust the pistons to morph it back into its perfectly parabolic shape. And you have to do that for like every position you can imagine on the sky, and then you build a lookup table. And so from that point on, whenever someone moves the telescope to that position, you just pull all the values from the computer, and the pistons, actuators, they adjust, giving you that perfect parabolic shape. So mirror shape control. Again, that's of the primary, and you only do it when you move. But it takes a long time to figure out how to do it well. And just to show you an example, this is an image from the New Technology Telescope. It's a European telescope that was built a long time ago in the 90s to test out these active optics technologies. And this is a picture on a pristine night. They're not using adaptive optics here. It just happened to be a really, really good night. Also, they're in the infrared. Remember I said go redward and you have less blurring. So this scale here is 5 arc seconds. So these things are maybe about 0.2 arc seconds across. Really, really good quality. And most nights are not this good. And this is when they have all their active optics systems on. So they have good airflow in the dome. They have the mirror temperature control turned on. They have the mirror shape control for the primary, and they can get a nice crisp image like this. But then you turn those 3 systems off, and this is what you get, about 1 arc second of blurring again, which is what we had been used to. Anyway, not the most exciting stuff, but stuff you have to take care of and do well. And so in the 90s in particular, we learned how to do this, and large telescopes have been retrofitted, and new large telescopes have been built with these systems already integrated. And once you do this, you can do the fun stuff, which is the adaptive optics. Let's come back to that. The untwinkling of the sky. And basically the way, maybe I'll go to a fresh sheet here. So adaptive optics, let's say we're looking at this part of the sky here, and there's a faint galaxy here that we want to image, but it's faint enough that we have to expose for many minutes, maybe even an hour, to get enough light to see it, to detect it. And during that time, we know the atmosphere is going to be moving it around, and so what gets saved onto our detector is blurred out. But if you have a bright star nearby, we call these guide stars. We can monitor that bright star. Suppose it's so bright that we can image it in 1/100th of a second. So we could put a video camera on that star, and as the atmosphere starts to push it this way, if we can detect that in real time on that time scale, 1/100th of a second, we can send commands to little mirrors behind the telescope that will push the light back to the same pixel on the detector. Then if it starts drifting this way, we push it back. So we're always lagging the atmosphere a little bit, but we can be fast enough that we can keep it on that spot pretty much. That means this galaxy also, even though we can't see it in individual frames, it's kept on that spot as long as it's close to the guide star. Let's say this is an atmospheric pocket. So if we can track a bright star in this pocket and keep it steady, everything else stays steady, and we can do long integrations. Let me show you an example of the movie animation. This is the Gemini Telescope again. And so what we're seeing here is the light going through the telescope, hitting the primary, secondary, going through the hole in Cassegrain. And we're gonna rotate into the adaptive optics module. And we're gonna zoom into it here. This is, of course, a simplification, but it gets the gist of it. So there we have our camera hooked up to a computer, and here comes the incoming light. And we're going to bounce it through a series of mirrors, basically. And without doing the adaptive optics, this is what we see. The star, it's bouncing around. Actually, you have 2 effects. One is the star moves around, and then you have the magnification, demagnification effect. This animation showing the latter. You can see the star is getting amplified and de-amplified. So what can we do about it? Well, here come the light. Here comes the light. And you see how it's distorted. This is representing the atmospheric distortions. These were originally flat, plain parallel rays of light. Now they've been distorted by the atmosphere. They're coming into our system. They hit these two special mirrors. I'll pause it there. This mirror down here is what we call a half mirror. It lets some of the light bounce and some go through. And it's going through to a high-speed camera. This is a video camera, and often we won't grab the whole image. We'll just grab the spot around the guide star. And we send it off to a high-speed computer. This camera is connected to a high-speed computer, which isn't drawn here, but just imagine that. And that computer is measuring how much the star is being pushed up or down or left or right, being magnified, demagnified. And then we send commands to this previous mirror. If you look at it, it's a deformable mirror. Now, most telescopes with adaptive optic systems, or AO systems, well, there are two types of mirrors you can use. One is tip tilt, like the SOAR telescope, 4-meter class telescopes, they just have tip tilt. It's a flat mirror, and if the star is drifting up, it bends the light back down. If it's drifting to the right, it bends it left. And so it's always moving, and the motion is really small. You can't see it with the human eye, but it's very fast, of course, like 1/100th of a second. So you see it there, and you can't see it move, but you can hear it buzz zzz, as it's doing these micro adjustments, keeping the star in position. But the really advanced telescopes, they have not just tip tilt. Let me write those two things down. You have tip tilt, that's your basic system, but your more advanced system can be a deformable mirror. That's what we're seeing here. The mirror is actually, do it under the dot cam, bending, and it's kind of weird, but distorting in exactly the way you need to undistort the atmosphere. See how they're coming out flat then? Now, as I said, there's always a little bit of a lag. We can't do this infinitely quick, so it won't be perfect, but we can get pretty close to the diffraction limit of these telescopes. You see how that cleaned up there? That's the basic idea. Wild space-age technology, though we have mastered it, and it's built into every large telescope. Custom, it's standard. It's standard now. So here's an example. This is taken with the Keck telescope. This is Neptune. If you're in the lab course, you took a picture of Neptune, and it was just a blur. It was a bigger blur than the stars, but it was a blur. This is, that's with like a 0.4-meter telescope. This is a 10-meter telescope using active optics. The active optics are turned on, but the adaptive are turned off at the moment. And you can see some structure. There's clearly Neptune. There's some cloud systems here. But now if we turn on the adaptive, again, you have to have the active in place. So active is on, adaptive is on, and you get this. Cleans itself up like that. And so you can see details of these cloud bands and storms, and this is just Neptune, but we can do many things as well. Let me see what's next. Oh yeah, last bit about adaptive optics is these guide stars. I said you need to have a really bright star within that same atmospheric cell. So if I want to look at any place in the sky, how often do you have a bright star close enough? And given today's technology, that we can we actually detect that bright star in 1/100th of a second exposure? No, we don't have enough of them all over the sky. So adaptive optics with natural guide stars, you can only do it on about 10% of the sky, because only 10% of the sky has a natural guide star close enough. Maybe the brightest star is over here. That's in its own atmospheric cell. It's moving this way. This galaxy might be moving that way. They're uncorrelated. So I can't use this star to help me keep this galaxy stationary. It needs to be within the same atmospheric cell. And if it's not, we can make one. We can take a really high-powered laser, shine it up into the atmosphere. And most of the light will go off into space, but some will bounce off the atmosphere and come back down, well, scatter in all directions, but some will come back down to the telescope, and it will look like a star in our image. And we can use it to guide off of. It's best when you have both, actually. Natural guide stars tell you what's going on in the upper atmosphere. These artificial guide stars tell you what's going on in the lower atmosphere. And so if you have both, you can really get some crisp images. But if you go to some major observatories at night, you'll see lasers coming out of the telescopes. And these are like serious lasers, like put your hand in front of it, burn a hole through your hand kind of laser. And in fact, you have to have, whenever you use them, you have to have spotters out there watching for planes, and you have to coordinate with local air traffic control and stuff like that, because you could blind a pilot with these. But anyway, we can use them and untwinkle the stars pretty much anywhere we want. Okay, so that's adaptive optics. Questions about any of that before I get into a tour of UNC's facilities? It's kind of the end of.
Can you explain one more time what the lasers do?
The lasers, yeah. So they go up into the sky. Again, most of it's just lost into space, but some of it will bounce off the atmosphere and come back to the telescope. And then it just looks like a star in our image. We're putting a star in our image. It didn't come all the way from space. It came from bouncing off particles in the lower atmosphere. As long as we have it perfectly aligned with where the telescope's looking, we end up with a star right there in the middle of our image. And so we can then use that, plug that into these adaptive optic systems. And as that fake star is being pushed around or blurred, we can track it, undo that in real time, and get crisp images. And that's called an artificial guide star. Let me write that down. So we have natural guide stars, and we can make artificial. Oops, try again. Artificial, yeah, artificial. So we have both. Okay, so before moving on to, we've talked about visible light telescopes, but we've learned about the electromagnetic spectrum. It's quite broad. The visible band is just a very narrow part. These visible light telescopes also work in the near infrared and the near ultraviolet, but as you move out to other parts, you have to use other technologies. And so we will spend some time talking about radio, because you could do that from the ground, and all the other wavelengths you have to do from space, and we'll hopefully get there as well on Friday. But I want to spend the time we have left going through UNC's observatories, because it's pretty special here. We're not the largest astronomy group, but we're a medium-sized astronomy group. We have maybe 7 or 8 astronomers, maybe 5 or 6 of them are observational. It's more than most institutions, but it's not like Caltech, where I did my postdoc, where they have 30 faculty and then 30 postdocs, all astronomers, that kind of thing. But we have a lot of observational resources. We have more observational resources per faculty member than any institution on the planet. I'm pretty sure that's correct. So let's just begin with, I'll introduce them kind of in historical order. Now, the first one's Morehead Telescope on campus. This is our campus observatory. And campus observatories, they're not meant for cutting edge research. I have done some research with this telescope. I've seen things, cosmic explosions, maybe about 2/3 to 3/4 the way across the observable universe, just from on campus. But it's a bright sky, in-city location. The atmospheric blurring, the seeing isn't great. It's here primarily for education and public outreach. But it was our largest telescope until 2004. It was built in 1974, the same year I was, I guess. And here it is from the inside. We're doing major renovations to it right now, both aesthetic, with new flooring and a mural on the walls and stuff like that, but also a renovation of the hardware. And once that's done, it would have been done by now, but COVID pushed us out for a long time. It will be connected to Skynet, so the same system you use in the lab. The way it works, it's a 2-meter mirror. Light comes down through the primary, or through the top, bounces off the primary, comes up, bounces off the secondary, comes down here through Cassegrain. Down here we have both a camera for research and a flip mirror. We can redirect the light out into an eyepiece for people to look through with the human eye, since it is also for education. And we have a guest night program, not during COVID, but once we start that back up again, you can just Google Morehead Observatory Guest Night and sign up. It's always on a Friday night. It's free. It's good date night. You go out and you can look at planets and bright deep sky objects. And sometimes they'll switch it over to the camera so you can see things that are even fainter. But that's where we were, and it certainly doesn't make us a cutting-edge research facility. But my colleagues started planning a major expansion all the way back when I was 12. It takes a long time to do this. And they finally built the first part of that in 2004, the SOAR telescope that I've been mentioning. It's at the same observatory as the prompt telescopes, well, the prompt telescopes are all around the world now, but our primary site is in Chile. You can see the prompt telescopes there that you'll be using in the lab course in the next week or two. Will regain access to this observatory. It was closed due to COVID. But on the other mountain, about 10 miles away, I've walked it, I've hiked it between the two. It's very high elevation, so you get sunburned very easily. I should have protected myself better. I ended with a terrible sunburn after that. But on the other mountain, we have a number of telescopes, including the Gemini Telescope that we've also been seeing, and the SOAR telescope, and this telescope I told you about before, the Rubin telescope, that's going to image the sky every 3 nights, is being constructed on this other mountain. This is the higher mountain, probably the better mountain. Anyway, the SOAR telescope, this is a UNC-led effort. Again, they started it when I was 12, and finally it was commissioned in 2004. Here it is inside the dome. It's a Naismith design. So the light comes in, bounces off the primary. You can see here the pistons, all those actuators. So the active optics goes up, hits the secondary that you can see a little bit of, comes down, hits a tertiary, which sends it out to the side. And we have a large optical spectrograph here, the Goodman Spectrograph, made at UNC by our Senior Associate Dean, Chris Clemens. On the other port over here, you have near-infrared instruments. So you can see visible light, infrared light, and then you have little ports all the way around. So that tertiary mirror can redirect light to any of those ports. And those ports, are smaller, sometimes student experiments. And this telescope is one of the reasons that attracted me to come here. Normally, well, the science I was doing, I was trying to find the most distant explosion in the universe. That's what my interest was back then. And to do that, you have to work in the infrared. By the time that light gets to us, if you're looking at visible light, by the time it gets to us, it's been stretched into the infrared. So I need a telescope with an infrared system, and one that you can turn that infrared system on like that. And also a telescope that can move into position very quickly. It's the things I was studying, these cosmic explosions called gamma ray bursts caused by the deaths of massive stars, they don't last very long. You may only have minutes. So I need a telescope that can salute very quickly, and this one does. And all the instruments are always mounted. You can just turn that tertiary mirror and suddenly you have an infrared telescope, even though the visible light observing was scheduled that night. Most telescopes, it doesn't work that way. It takes a whole day to switch the instruments. So this was very attractive to me. I came here and used it to, let me see what's next on my slides, if that's it. Lost my position, almost there. Yeah, yep, that's it. And used it and did just that. Got a little animation here. Once you do stuff like this, NASA will make these animations for you. So exploding star, and the light is very directed, happened to be directed towards Earth, picked up by a space satellite that sent the coordinates down to us, took over SOAR. This was 2005, so the telescope was just finishing its commissioning. It had barely been used, and so you can see the fading away object there that I later confirmed using the prompt telescopes, and Gemini was 12.8 billion light years away. The universe is only 12.9. Universe is only 13.8 billion, so I broke into the first billion years of cosmic history. And then use that success to raise a lot of money to expand prompt into a global network. Anyway, that's the SOAR telescope. I've barely used it since, actually. I only need it for that one thing. And since then, I've been busy on my Skynet telescopes. So I'll turn to them in a second, but let me just briefly show you our other very large system. This is the South Africa Large Telescope in South Africa. SALT is the acronym. This is actually a drawing of it from before it was built. It was built around this time. And this is how you do a Keck on the cheap. So it's like a 10-meter class telescope, but Keck costs $100 million. This costs $30 million. And we saved a lot of money by limiting it in the following way. If you have that mirror, and it has to be held perfectly still to fractions of nanometers, no matter where you point, very challenging. So we just don't tip it. It's designed not to tip this way. It can rotate, but it's maintaining its same angle with respect to the ground. So gravity is always pulling on it the same way. And this is limiting. You can't look at anything in the sky. You've got to plan. When it's rising, then you move the telescope to that position. You catch it when it's rising, and then you can catch it again when it's setting. You have a brief window both when it's rising and setting. So it's Q-scheduled. Everything is planned well in advance. It's primarily a spectrograph. It's really not for imaging. And it's kind of cool how it works. Maybe I'll draw this here. You know, it's only perfectly in line with the telescope for an instant. And you need more time than that. So here's your primary mirror. And here I can show you a picture of what it actually looks like. There it is. And at the top, instead of having a single focal point, you have a track. And when it's first coming into view, you put your camera over here, and it's looking using only this part of the telescope, looking in that direction. When it's directly overhead, you use the full telescope looking up. And when it's over here, you use this part of the telescope looking in that direction. I exaggerate the range that you have. It's still a really narrow band, but it means you can observe for about an hour. So the mirror is a giant hexagon, or a bunch of hexagons put together. And then early on, you're just using a little bit of the telescope, but then you're using more and more, and then the whole thing, then less and less and less. And it's 11 meters from corner to corner, but since you don't use the full thing all the time, overall it's about a 9.1 meter telescope, making it tied for 4th largest on the planet. And we're a 3% partner in that. So, and not a major partner, but if sometimes we need a telescope bigger than SOAR, maybe we're discovering something with SOAR and it's getting faint, we can turn to SALT and schedule an observation. With SOAR, I forgot to mention, we don't own that fully. We're the founding partner, but it's a $35 million effort, and so we had to bring in other partners, Michigan State, the country of Brazil, and the National Optical Astronomy Observatory that runs it for us, representing US astronomy. So anyone in the US can apply for time on it as well. Okay, so it's Morehead, SOAR, and SALT. And next, there are 2 other systems, my Skynet system and the Everyscope system, but I don't have time for that, so I think I'm gonna let you go 2 minutes early this time to make up for all the times I went 2 minutes over. I'll pick up with that next time and also talk about radio telescopes.
I have a question.
Yeah, go ahead.
So what's like the most recent big observation they've done at SOAR? Like what's been the most recent, like exciting thing that's happened with SOAR?
Probably the most exciting thing recently was a teaming up of Prompt and SOAR. And it's one of the things I'll talk about with Prompt briefly. But in 2017, we discovered the first optical counterpart to a gravitational wave event. This is something Einstein predicted, that like merging stars or binary stars going around each other very quickly as they're in spiraling and merging, they actually send ripples through the fabric of space and time. Crazy prediction. But Einstein made all sorts of crazy predictions, all of which have turned out to be true. So they started building devices to detect ripples in space and time. I'll show you some pictures next time. And the US government and the European Union, we have 3 of these detectors now, 3 places in the world. And in 2017, they detected in-spiraling neutron stars. These are dead remnants of massive stars, and said it's coming from somewhere over there in the sky. And then I turned my Prompt telescope one of them anyway there, and imaged every galaxy in that part of the sky until I found it. Found the first visible light signature of a gravitational wave event. And then once I found it, SOAR followed up because they then knew exactly where to look. I found it for SOAR basically. And they did spectroscopy using the Goodman Spectrograph that we built at UNC. And this has been a major prediction of Einstein. They spent 40 years building the detectors to figure this out. And the paper it's the most authored paper ever in astronomy. There are 4,000 authors, of which you see that in particle physics, where they have these particle colliders. Those papers often will have 4,000 authors, but not in astronomy. But this one, probably 1/3 of all practicing astronomers contributed to this effort. And UNC played a major role in being one of the groups. A number of groups discovered it simultaneously. We were the second of 6. But then we did the follow-up with SOAR. One thing I should say, and I hinted at this, a lot of telescopes given the number of faculty, and I haven't even shown you all the systems yet. That means undergrads can actually use these. If you go to Caltech, the postdocs don't get a chance. Well, the postdoc, faculty get time, postdocs get some time, grad students, if they're lucky, and undergrads, nothing. But here at UNC, undergrads can be using these systems. And so if you are going to be a major or a minor, get involved and start knocking on doors, or at least once COVID's done. Until then, start sending emails. Get into these research groups, and you can actually use these facilities. Other questions?
I had just a curiosity that I was wondering whether you had the answer to. You were mentioning Hubble and how it hasn't been able to be repaired because the spaceships or the shells that have been used to repair them in the past are no longer in use. Will that be changed once groups that are creating now their own private space shuttle programs are more advanced, say like SpaceX, which is now doing significant research? Will that affect that? Will that have a positive impact on, say, Hubble repairs, or will it still be taken out of commission in the next decade or so?
In theory, you could. You could commission a SpaceX launch, but that's not going to happen. Instead, they've spent the money building the next generation Hubble Space Telescope, called the Webb Space Telescope. We'll learn a little bit about it, though. That may actually be part of the video assignment. Webb graduated from UNC, and ran the space program during the moon shots, a long time ago. And so this observatory is named after him. It's a 6.5 meter diameter optical telescope, goes up into space and unfolds. But it will be off at one of the Lagrange points. It won't be in low Earth orbit. It won't be serviceable. It'll probably be a 5-year mission, longer if it continues to function. But the money is going to go there. Hubble's been great, but we've been using it for 30 years. It's time to build bigger and better systems. And we'll probably keep using Hubble even after that goes up until all or most of the systems die. It's just not worth it financially to keep doing so. I know a lot of people have an attachment to it because it's been here so long. It's been here your entire lives, and most of mine even. But it's very unusual. That's not how these things are supposed to work. Normally they're 5-year missions, 10 if you're lucky, and then you want the money invested in the next newer, better thing.
Just because this thought popped into my head, what happens when you've done that so many times that you end up with a situation almost like in the movie WALL-E, where you have so many satellites or systems out there that it's completely cluttered in space junk?
Or the movie Gravity, which is, the physics of it's totally insane and not at all right, but great movie, awesome movie. We have to be careful of space junk, and we track it even down to tiny little pieces. We keep track of where everything is and where it's moving. We haven't kept track of all of it, though, and occasionally, like the space station can get hit. And in fact, I think they have a little air leak now. It could be some kind of micrometeor or some piece of debris that struck it, and still a lot of space up there. You do want to keep track of this stuff, and at some point we may want to clear it. But with these large missions, it's different, though. come the end of the mission, we deorbit them and bring them back down to Earth and crash them into the Pacific. There's a certain graveyard in the middle of the Pacific that we keep putting stuff. Also because they're heavy, if they're in low Earth orbit, once the orbit degrades and gets in the atmosphere, it can come down pretty quickly, and we'd rather decide where it lands than let it go to chance. Because something as big as the Hubble won't burn up, it will make it down. And you know, large population centers like Mexico City and stuff like that are under the flight path.
You
So
can target it for our enemies.
Hmm?
You can aim it at our enemies.
Aim it at our enemies. Yeah, that's interesting political idea.
It's like
there.
the Zeus. Have you heard of the Zeus
No.
theory? It was like some obviously not an actual scientist, but some guy just theorized that if you had like a satellite or in low Earth orbit with large tungsten rods, you could like drop them kind of like missiles from orbit, and you wouldn't need fuel. So
Yeah,
it's kind of like that. Yeah.
explosives or anything by the time they hit the ground. That
Yeah.
My stepson, he called me this morning. He was going to work, and he saw a big fireball coming down out of the sky, which one of those green meteors that go across the entire sky. I've only seen one in my entire life, and it's probably only the size of a baseball. But yeah, if something the size of a baseball can do that, then yeah, you could drop stuff and it can make it down.
So if NASA typically like will take an object out of orbit and make sure it like lands in a specific place, was like the Skylab, was that like an accident or something, or is this like in response to Skylab crashing or coming out of orbit and burning up in the atmosphere?
Skylab was a long time ago, and I'm trying to remember if it was a controlled descent or not. Back my memory, thinking it was not a controlled descent. Once it was done, I don't think I don't want to say because I can't remember if it was just the orbit decayed and there's nothing they could do, or if they brought it down on purpose. Do you remember, or do you know? It was before you.
I don't know exactly. I feel like it wasn't controlled because I remember hearing something about like it landing in the middle of Australia, but I'm not sure.
Yeah, I'm trying to. I think you're right. I should know this stuff. Because I actually go down and hang out with some of the old astronauts about once a decade. They paid for a good chunk of my undergrad, and so as an alumnus of that program, I get to hang out with like Buzz Aldrin and stuff like that. And so I'm supposed to know all this stuff, but I've forgotten about Skylab. I think you're right. I think it scattered across parts of Australia. Anyway, that would not be a controlled descent. Other questions? All right, good class. I'll reset for the next one. See you Friday.
Thank you, Dr.
Thank you.